Hi, in the second part of this multiple regression video, we'll start with looking at our least squares beta estimates and understanding some of their properties. So remember, we were trying to project a y vector onto a space as best as we could, and that will therefore define the best beta hat estimates that we can. What are some of the properties of estimating things in this way? Well, we're going to do and study what's the typical behavior, what's the average that these estimates will be if we repeatedly take samples, what's their expectation, and what are their variations going to be. Remember that the estimated variation is going to be a standard error, and you make standard errors by simply finding the variance expressions and substituting in our estimate of the error variation sigma. It turns out, very fortunately, that on average our ordinary least squares beta estimates turn out to be on average exactly what they want them, what we want them to be. This is called unbiasedness. Our estimates are unbiased. On average, the estimates tend to be the values that were used back in the original data creation system. The variation has a more complicated formula. The variation of our estimates are, notice it involves the variation in the data creation process, and that should make sense because more variation in the data system should give us more uncertainty and variation in our beta estimates, and it does. And then we have this X transpose X inverse matrix, which, if you think about the dimensionality of this, it's going to be a matrix or a table that's going to be P plus 1 rows and P plus 1 columns. And it's basically going to be a matrix that keeps track of the variations for all of our estimates. And in fact, going down the main diagonal is going to be the variance of every one of our betas. The first row and the first column of this matrix is going to be the variation of beta naught hat. The next row and column, so the second row and second column, is going to be the variation of beta 1 hat, and so forth, down to the very last row column diagonal, and that'll be the variation of beta hat P. Because those things involve X transpose X inverse, it's only a function of the predictor variables and how many there are. So it's a very complicated expression, and there's a lot here that is hard to understand. It involves the interrelationships between the predictors and each other, and it also involves the sample size. Standard errors are just found by going down the diagonal of that matrix that I mentioned and taking the square roots of those diagonal elements using sigma hat squared. So for example, in this model output for a multiple regression model, the column called standard error is going down the diagonal of a variance matrix, plugging in an estimate for the error variation, and then taking square roots. So here's how you specify a multiple regression model in R. It's the LM command. The response variable here is fuel. We're going to use income, tax rate per gallon, and DLIC, which is, remember, the fraction of licensed drivers, and then log mileage. And we're going to make a model object M99. And then I'm just going to show you the coefficients part of this. So beta naught hat is right here, the 154.19. Beta 1 hat is the negative 6.135. Beta 2 hat, beta 3 hat, beta 4 hat. Here are the standard errors for each of the coefficients. And so in this overhead 38, we go through that same content and we do the interpretations. Now the intercept is not usually interpretable, because we usually will never ever have a case where income and tax and mileage are all zero. So it really doesn't make much sense to talk about the estimated intercept, and we usually don't bother. But the other coefficients are important. So for example, holding all the other predictors constant, what does negative 6.135 for income, what does it mean? Well, it means that if we increase per capita income by 1 unit, which is $1,000, that is associated with a 6.14 gallon decrease in fuel consumption per person. For tax, if we increase the gasoline tax by a cent per gallon, we would associate that with a 4.25 gallon decrease in fuel consumption per person, holding all the other predictors constant. Similar sort of interpretations for the other variables, DLIC and mileage. Note that the mileage effect is difficult because if we increase log miles by 1 unit, remember this is in log scale, but it's base 2, and that means you would interpret 18.5 as if you increase the miles, not log miles, but if you increasing log miles by 1 unit means, because it's log base 2, that we will double the highway miles. So this number is interpretable as if we doubled highway miles, what would the impact be on fuel consumption per capita? Well, it would be an increase of about 18.5 gallons per person, all else, all these other factors held constant. So please note that that is how you interpret a coefficient where the predictor is in the log scale. One of the things we'll be interested in doing is making statements and doing inference for one beta parameter at a time in our multiple regression model. And we'll be using t-tests and t-confidence intervals to do this work. And if we have either a reasonable amount of data or reasonable residuals to have errors normally distributed, we can make confidence intervals and tests like this. The thing you need to know about the t-distribution here is the degrees of freedom will be n minus the number of beta parameters. Remember, there are p betas, beta 1 to beta p, for each of the betas multiplying a predictor, and one extra one for beta naught, the intercept. And so the degrees of freedom for all of our t statistics and confidence interval multipliers is going to be n minus p plus 1. Confidence intervals are just going to be estimates plus or minus an appropriate multiplier times standard error, and hypothesis tests are going to simply be the beta hat estimates minus a hypothesized value from the null hypothesis over a standard error. Confidence intervals can get constructed using the confint command, and you put in the model object, confidence interval you want, and you will come up with confidence intervals like this one. And how would you interpret something like this? Well, let's interpret let's interpret log miles. What we would say about this is, because all of the plausible values for the beta 4 parameter for log miles, the beta 4 parameter, all reasonable values seem to be positive, and that means there is evidence that the true underlying data generating mechanism has a beta parameter, beta 4, that's positive, and that suggests increased fuel consumption per capita when the log miles increases. And that's how you would do a conclusion for a confidence interval. Notice for all of these, every beta coefficient seems to be significantly different than 0, suggesting that each of these predictors has a notable effect on fuel consumption. If we want to do a hypothesis test for a particular beta parameter being 0 against an alternative hypothesis that it's not 0, realize that that means the null hypothesis says that the mean function doesn't depend on predictor xi, and the alternative hypothesis says that it does. For a predictor like income in the model we've just dealt with, our income, remember the predictor, the beta hat is about -6, the standard error is 2.19, and that gives us a t-statistic as in the output. And so when we construct and put in the beta hat, divide by the standard error, we get a -2.796 t-statistic. We use the p-value from the output. We have n minus 5 beta parameters. Remember, we have 4 predictors plus an intercept. There's 51 states and District of Columbia, so there's 51 observations. Minus 5 gives us 46 degrees of freedom. And notice the p-value from our output is almost my favorite p-value of 0.007. Very small chance that we could observe a beta hat system as we have, given that the null hypothesis for income really is a 0 effect. It would be very difficult and very unlikely to ever observe a beta hat statistic like we have here if income really had no effect on fuel consumption. And that brings us to the conclusion that we have here in overhead 43. The small p-value means there's lots of incompatibility between the observed data and the null hypothesis. That leads us to doubt the null hypothesis and support the alternative, that fuel consumption really does depend on income. And because we have a negative estimate for the beta hat, we've got evidence that the effect of income is that increased state incomes are associated with decreased fuel consumptions per capita, holding all the other state characteristics constant. The coefficients that we see in our multiple regression output have a connection to the red slopes that we see in added variable plots. So I'll remind you of the model we dealt with earlier that used income and log miles to explain fuel consumption. You'll recall there was this negative impact for income and positive impact for log miles. And the thing you need to know about added variable plots is that this negative 7.44 slope for income is actually the slope of this red line in the added variable plot for the income added variable. The 18.67 for log miles is the slope of this positive red line in the log miles added variable plot. So you need to know that the slopes and the beta hats that you see in a multiple regression output set are the slopes in added variable plots. On overhead 46, I'm showing you 3 different models, and I want you to notice the slight differences in all the coefficients. So in the first model, that is our MLR2 model that has both income and log miles in it. This second column is model 2 that had only, its inc mod, only had income, and the third model only has log miles. And so I want you to look across the coefficients and notice what happens. In the model with both predictors, income's beta hat is a negative 7.44. But when income was in alone, it was a more extreme negative value. It was a negative 9.28. But when we added log miles to the model, the income effect was moderated and it was a little bit closer to 0. Notice that the log miles effect is 18.67 in the model that also has income. But in the model that only had log miles, this was a much bigger number. It was 25.25. And so you can see that the coefficients for income and the coefficients for miles are similar. They're just a little bit different when you add another variable to the mix. And this is an important general finding for multiple regression models. When you add other predictors to the model, individual coefficients will change because of the interrelationships between income and log miles. Notice down here on r squared, we had the 0.178 r squared when only mileage was in the model, and 0.216 when only income was in the model. But when we put both of them together, we get a 0.304. Notice that 0.304 is not the sum of these two r squareds. It is somewhat less. There is some overlap between what income and log miles can explain. And that is the basic principle of how multiple regression works. Next, we're going to talk about the concept of r squared again. And its general definition is just the explained part of variation in the response that's being explained by the predictor set or the regression model. Before, it was the fraction of variation that was explained by the fraction of response variation that was explained by a single predictor. Well, here it's by the set of predictors, and we interpret it the same way. From our big multiple regression model, we can see r squared right down here, 0.51 for this 4-variable model, and the implication would be that our predictor set, our model, explains about 51% of the variation in per capita fuel consumption. The estimate of sigma is right here under residual standard error. 64.9 gallons per person is the typical variation in states' fuel consumptions around the mean function. And now we come to the methods for predicting a particular response value y. And we have the similar distinction that we need to decide, are we going to be trying to estimate the mean function, the typical value of y when the predictor set is capital X, or are we interested in estimating a single value of y? And so the first bullet is talking about the notation and the ways in which we might be interested in coming up with confidence intervals and point estimates for a mean function. Basically, if you wanted to come up with a point estimate, what you would do is you'd plug the observed value of predictors, little x, into this estimating equation with the beta hats and come up with this linear combination or fitted value, y hat. You will do a similar thing with a prediction for a single value of y, but remember we use the notation y tilde star to designate the fact that we're going to be interested in a single value of y rather than the mean function. If you're interested in estimating the mean function, the standard error is this formula. It's just the estimated sigma variation times the square root of a linear combination of the observed data values for the predictors, little x, and the overall variance matrix, x transpose x inverse. We saw this earlier as part of the beta hat variation. Because remember, what you're finding the variation for here is this linear combination. And so what we're really doing is trying to appropriately measure the variation in these beta hats. And this is the expression that does that, appropriately weighted for where the values we want to predict at. So what's involved in this variation? Well, the variation in the data system, sigma, how well the beta hats are being estimated, which is being controlled by x transpose x inverse. And it also matters how strange or how weird predictor values we want to estimate the mean function at, little x. if you want to come up with an expression and come up with mean function estimates and variations, you use the predict command with the interval equals confidence option. And what I've done here is I've come up with a new temporary data frame called new data that has two sets of X predictor sets in it. The first one has income of 28, tax of 20, DLIC of 909, log miles of 15. And that's one predictor set that I want to estimate the mean function at. My other predictor set is 28, 35 for tax, 943 for DLIC, and 16 for log miles. And I come up with estimated mean functions of 605 gallons per person for the first set, 576.1 gallons for the second set, with confidence bounds lower and upper for each one. If I'm interested in just a single value of the response, there is a slightly different formula. The standard error of prediction is given like this. It is very similar to the formula you saw for the mean function, except an extra multiple of sigma squared, because we need to incorporate just the random y variation in the expression. So it is the standard error for the mean function, SE fit, plus an additional sigma hat squared multiple. And so the same things that drive the variation of a prediction for the mean function drive the variation for a predicted value of y. If you want to estimate, an individual response value like fuel consumption in particular state with state characteristics, you can do it with the predict command interval prediction option. And here I'm thinking about states, two separate states, one with income characteristics 28, tax 20, DLIC 909, and log mileage of 15, whatever state that is. I would estimate the fuel consumption per person to be 605 gallons per person, and my boundaries, my confidence boundaries for uncertainty, to take me from about 473 gallons per person up to about 737 gallons per person. And so that would be the appropriate variation for this state. I did a little computation down here to illustrate what I'm doing to get this 722 gallons per person upper boundary. Notice that these confidence bounds for an individual state's consumption are substantially wider than for the mean function for the equivalent states. So back on overhead 51, the confidence bounds for the mean function are quite a bit more certain about what's going on than what will happen for an individual state. And here is some R coding if you wanted to predict individual value of fuel consumption for a single particular state, not a set of two states. I wanted to make sure you understood how you would put in the values just for one observation. You can do a extension of these ideas to just a linear combination of model coefficients. You'll see this later in the course, but sometimes what you want to do is have a function of the betas, and it will be meaningful to whatever problem you're studying, maybe like the difference in some predictors. And you can construct an arbitrary function of your betas, and you can estimate that arbitrary function by putting in the beta hats, and you can estimate the standard error of that function. I'm saying the function is this this symbol lowercase l, and the function L can be estimated by putting in estimates of the betas, and you can get standard errors by this kind of complicated linear function. And I'm going to be showing you how to do those in future. Finally, as in all models, we can look at residuals and residual plots. And we're going to spend much more time on this later, but a typical residual plot that will help you understand what's happening is to have residuals from your model on the vertical axis and predicted values, or y-hats, on the horizontal axis. And what you're hoping for is random scatter above and below 0 for the residuals without any particular patterns. And so here's the coding for predict on the horizontal axis, residuals for a model on the vertical axis, and you can see they basically evenly scatter around 0, suggesting no real problems with this particular model. A point up here means that, well, whatever this state is, I think it's Wyoming, has a substantially higher actual fuel consumption per person than what we would estimate. A state down here, I'll be showing you how to find out what cases these are, but this state has notably smaller fuel consumption than what we would expect from our model. Let me know if you have questions with this.